And hello, welcome everyone. Welcome back to where we are talking about. So last video I was talking about something about sampling rate and sampling frequency. Yeah, sampling rate and sampling frequency. We are talking about, if we have an analog signal, the higher your sampling rate, the higher fidelity your signal, right? The closer your bar charts over here, your bar chart signal will actually resemble your analog signal. So for audio, your standard sampling rate is about 44,100 44,100 hertz or 44.1 kilohertz. All right. So how did I know it's 44,100? If you take a look, this is Audacity. Okay, you need to install it, and I'm pretty sure there are lots of videos on YouTube. How do you install Audacity? Okay, how do you install Audacity? You can go to audacityteam.org. This is open source software. Okay, so you go to audacityteam.org, you download Audacity. Alright, so this is free open source cross-platform audio software. You can use it for Windows, Mac or Linux. So I'm doing it on Linux. So this is what I have here. So basically it hooks it up to your microphone and it starts recording audio. Okay, just like I'm recording video, but I'm recording myself recording audio in a video, if that makes sense. So yeah, I think hopefully that makes sense. Alright, so it basically hooks up to your microphone and it's able to record audio, sorry. So how do you know it's 44,100 hertz or 44.1 kilohertz? So if you go to edit preferences, okay, edit preferences, and you go to your quality, alright, you'll see that the default sampling rate is 44,100 hertz. You can see this, 44,100 hertz. So this is how often you have your digital sampling. It is 44,100 times a second. So that's pretty darn quick. But of course, this is your standard audio quality. Sometimes audio quality can go much higher, like 48 kilohertz or 88 kilohertz. I mean, some of the options that you will see here are not just the 44,100 hertz. You can go lower to as low as 8,000 hertz, or you can go all the way up to 38,400 hertz. Okay, so the more hertz you have, the higher frequency you can capture. Alright, the higher frequency you can capture. Alright, so the process of recording, let's say, a sound will be like so. You set your frequency to about 44,100 hertz, and you start. That was my chair. Yeah, you start pressing the record button, and okay, I should not record myself talking. Let's delete this. Yeah, you start pressing the record button when you're ready to play a note. So I'll play the note A. Okay, I'm going to use Lingert to help tune my guitar. Slightly sharp, and notice the frequency as I'm tuning. Yeah, so you notice A is about 110 hertz, and this A is one octave up. About 220 hertz, and this A, another octave up, is about 440 hertz. So sometimes your A's may be tuned slightly differently in terms of hertz. Some people like 432 hertz to be your standard A. Some people like 440 hertz, but this tuner tends to work at about 440 hertz. Okay, so let me play an A and record it on Audacity. Okay, So let me go. Okay, so that's the A. Okay, let me take out the silent portion, and I'll just press delete on the Audacity. Then when I'm done, I just select this part and I'll export it as a WAV file. Alright, so this is A. What A is this? I can't remember. It's A2 at about 110 Hertz. So let's do A2, 110 Hertz. So this is how I record my Audacity files. It's very simple process. So after that, you will see the spectrum. If I load this file, you see the spectrum slightly shift. Yeah. So I'll load the A2, which is 110 Hertz, and you will see that there will be peaks, slightly different peaks. Okay. Okay, one at about 110 Hertz, as you can see here. And if I change the fast Fourier transform size, okay, you see another peak here at about 110 Hertz, which is what the A2 is supposed to be. Okay, so this is how I know that my sampling frequency is 44100 Hertz. I mean, that's the way I set it in Audacity, and that's usually the default setting for a lot of audio files. Though not all audio files are the same, at least for this one, it is 44100 Hertz. Okay, so that's how you can actually determine your sampling frequency. Okay, I mean, the other way, since you have this power spectrum tool, is that you can check the frequency. I mean, you know your frequency is about, the A frequency is about 110 Hertz. Then you make sure that you change the FFT size such that you have a peak here at 110 Hertz. So when I switch it to 44100, it is 110 Hertz. You will see that peak. And that's how you know that 44100 is the actual size, or the actual sampling frequency. Okay, so this is how you can actually get your frequency bins to correspond to your sampling frequency. Now, here's the deal, right? Let's say you don't know that this is your sampling frequency, and I change my FFT size to -1, which means that Labview will take the whole array, your whole array, to be that frequency, that size. How then do you determine, right? Okay, let me do it around maybe 1500. Okay, you notice the peaks here are about somewhere at 270, 275, right? So this is not going to correspond directly to Hertz. Now how are you supposed to make it work? Alright, how are you supposed to make it work? Okay, so there are a number of ways. Alright, so there are a number of workarounds. Okay, remember we were talking about this sampling frequency. Okay, we can see this frequency resolution, or the frequency spacing between the components of Y, or the frequency spacing between these frequency bins, between, let's say, bin 249 and 250. What is the number of Hertz changing between 249 and 250? It is going by this formula, which is the sampling frequency over N. Okay, let's see. How do we calculate N here? We don't see the array size directly. We can use Labview to check the array size, or we can use it like so. We can think of it this way. So delta F, right, equals to, okay, you have your sampling frequency over your FFT size. Oopsie. FFT size. Alright. And what is this equals to? So this is your sampling frequency times number of samples, right? What is the number of samples here? number of samples is actually your time of your audio file times how many times you sample the audio file per second, right? So this is the time elapsed for your audio file, and then this is how many times you sample per second. So you multiply this together, you will get the total number of samples. So this is the whole FFT size of the array. That's if you take your whole array to be your FFT size. Okay, so if you take your whole array to be your FFT size, how do you determine this? Well, looking at the formula here, you have Fs on top, Fs at the bottom, both of which are sampling frequencies. So one easy way is you notice that delta t is all that remains at the bottom. So that's a very convenient thing. So okay, take a look at your audio file. You notice that it will end approximately, okay, here you see in this, this is my audio graph. Okay, this is my audio graph. It will end approximately at 3.5 seconds. The A note ends at about 3.5 seconds. That's how long the audio file is. So take note of that, 3.5 seconds. So if we note that 3.5 seconds, this delta t here is 3.5 seconds. So you find that the frequency resolution is 1 over 3.5. This is the delta f. So if you have 1 over 3.5 to be your delta f, what then is the frequency at frequency bin? Maybe look at this here. Between 250 and 500, this is about 375, right? Yeah, they're about 375. So let's say a frequency bin 375. What is the frequency here? Okay, so the frequency here equals to the frequency bin 375 times delta f. Okay, because it has shifted 375 times from frequency bin 0. Okay, so 375. So this is a very crude way of estimating that frequency peak times 1 over 3.5. Okay, so let's do it here. So 375 divided by 3.5. What do you get? 107. Now this is pretty close. This is pretty close to 110 Hertz. Okay, it's pretty close to 110 Hertz. Okay, so that will approximate where your frequency is. That is, of course, if you can read this time data very well. I just estimated it at about 3.5 because it does look like 3.5 here, right? It's somewhere between 3 and 4. Of course, you'll need to zoom in a lot more in order to get the correct timing resolution. Okay, how else can you check your FFT size, so to speak? Okay, so there are a few things in Labview that you can do. Namely, you need to start playing with arrays, and you do something about. There's a way to check these arrays using the array size. So just right click. Okay, right click the array. There's this tool here called array size. Okay, so click on this array size and go here. Okay, so let me go show you again. Right click, go to array, and click on this VI called the array size. Okay, so you need to feed in some data into this array size, and then you need to output. So how do you create the data output here? Okay, so what I did is to feed this FFT array. Since my FFT size is -1, it will just take the whole matrix or the whole array from my audio file, and then it will transform it into the same n number of frequency bins, which is what I was explaining in prior videos. Okay, it will take an n-sized array and transform it into n-sized frequency bins. Okay, so oopsie. Press the escape if that ever happens. If you accidentally click on the spool again, if you actually accidentally click on the spooling data and you want to escape this dotted line thing, just press escape. Alright, so anyway, I want to output the array size or something like that, right? So what you need to do is to create, okay, go to the part that says size, the output, go to the output of this VI, or this mini VI or this mini box, whatever you call it, go to create and you click indicator. Okay, you click this thing called indicator. So this is where your size will come out. So you see this new thing actually pop up. It says size of S. Okay, so I can change it to size of FFT. Okay, FFT size using array size. Okay, and then this thing, just for the sake of not confusion, how many samples to take. Okay, I will call this FFT size. I'll say how many samples do you actually want to take. And then this is FFT size using the array size. So this is how I sort of differentiate it. Okay. So FFT size, the array size, I'll just press run and you'll see that this FFT size is about 155,000. You can see here 155,000. That's using the array size to help us determine what the FFT size is. Of course, you can take a look at the number of frequency bins here. You will see it's about 150 something thousand. It's between 140,000 and 160,000. This is the last frequency bin. But anyway, your FFT size here using the array size is much more convenient. So you can use it to point it to about 155,000. So if that's your actual size, let's kind of take a look at it, right? Okay, 375-ish times 44,100, that's your sampling frequency. Then you divide it by your FFT size, 155,001. So you will get about 106.69. Why is it like that? Well, I mean, it's a bit hard to see what this actual peak is. It's about 375 or 380. Okay, so I'll need to actually zoom in to see where this peak is actually at. So I'll put about 380 and let me change this to about 390. Okay, so you can see that the frequency bin is not 375, it's about 388, 387. So let's put 388. Okay, you see 388 to be your actual frequency bin. And then you multiply by 44,100, which is your sampling frequency. You divide by the array size, which is 155,001. Okay. When you do that, that actually makes it read that this frequency bin at 387 or 388 that actually corresponds to 110 Hertz. So that's how you use your fast Fourier transform graph to read off the frequency if you want to use the full array size to be, you know, your thing. Okay, so 300 here, maybe 450. Okay, so you can see that this peak here can be read as 110 Hertz because it's at the 388th frequency bin. Okay, so excuse me. Yeah, sorry about that. Anyway, so that's all I have for you this video. If you want to automate this process, you'll need to do a few more things. Yeah, not just use this array size. You'll probably want to kind of give it the individual. You need to do some array manipulation, which I won't go into depth in this video because time's almost up. But yeah, hopefully this is helpful for you to understand how this frequency bin actually relates to actual frequency. Okay, so thanks for watching. I'll see you guys again.